Welcome back, students. We have been discussing the temperature coefficient of resistivity, and we also did a problem in the previous video, example 3.3. In this video, we will do example 3.4 and then continue to discuss the rest of the lesson. Okay, example 3.4. The resistance of the platinum wire of platinum resistance thermometer at the ice point is 5 ohms and its steam point is 5.23 ohms. When the thermometer is inserted in a hot bath, the resistance of the platinum wire is 5.795 ohm. Calculate the temperature of the bath. The resistance of the platinum wire of a platinum resistance thermometer at the ice point is 5 ohms and its steam point is 5.23 ohms. When the thermometer is inserted in a hot bath, the resistance of the platinum wire is 5.795 ohms. Calculate the temperature of the bath. So that is the problem. So there are three temperatures we are talking about. One is the ice point temperature, and the other one is the steam point temperature, and then the third one is an unknown temperature. Okay. Ice point temperature, you know, it's 0 degrees Celsius, 273 Kelvin, and the steam point also, you know, it's 100 degrees Celsius, 373 Kelvin. And the other temperature is what you need to find out. And they've given you three resistances. Okay, one of the things that you have to assume here is that the temperature resistance of the temperature coefficient of resistivity, alpha, is going to remain the same over this range. Okay, it is. I told you already that that alpha could change for a material for different temperatures. The temperature coefficient of resistivity also could change. It's not a constant number for one material. One material may have one alpha at one temperature and a different alpha at a different temperature. But we are going to assume that over this temperature range of steam bath to whatever temperature that we need to find out, the alpha remains the same. Okay, so the alpha remains constant, and then the temperature increases. Okay, with that assumption, we will go ahead and do this problem. Okay. First one, in this example 3.4. First is ice point. Then the resistance of the temperature is given. I'll call this as R naught, and that is going to be 5 ohms. This you know. And what is the temperature at ice point? Temperature is actually 0 degree Celsius or 273 Kelvin. Either is fine, because we will be interested only in the temperature difference, so it doesn't matter. Then the second piece of information is this. At steam point, R naught is given to be R1, I'll call this as R1. It's a different temperature, right? So 5.23 ohms. Then what's the temperature there? I'll call this as T0, I'll call this as T1. It's going to be steam point 100 degrees Celsius or 373 Kelvin roughly. Okay, and there is a third piece of information, that is a hot bath. Okay, the resistance is given, I call this as R2, that is given to be 5.795. Temperature T2, we don't know, we are supposed to find it out. So this is the problem. So what did I say? I'm going to assume that the temperature coefficient of resistance alpha is going to remain the same, constant across this temperature range. Okay? So if that is the case, then I can use that equation. R1 is equal to R0 into 1 plus alpha delta T. I can use that, right? I'll do that now. So what do I know? I know that R1 is equal to R0 into 1 plus alpha delta T. Okay? So what does, I mean, I can take anything as R0. There's no fixed thing actually, okay? So it looks like, so you have a linear relationship. Alpha is the same, so you'll have kind of a constant, so you'll have a linear relationship between R1, R2 and R0. So it doesn't matter which one you are going to take as R0. Okay? Any resistance can be taken as R0 and the rest could be worked out. Okay? So I'm just going to take this as R0. So I'm getting this. R1 is equal to R0 to 1 plus alpha delta T. What is R1? R1 is 5.23 ohms is equal to R0 is 5 ohms into 1 plus alpha I don't know right now. And what is delta T? Delta T is the temperature difference, T1 minus T0. So that would be 100 minus 0, 100 minus 0, or 373 minus 273 Kelvin. Either way, you're going to get 100 only. Okay. So that gives you 5 into 1 plus 100 alpha. Okay. So I can expand it. It will become 5 into. This will become 5 plus 500 alpha. So, okay. I'm multiplying it, taking it and multiplying it side. So I can bring this 5 to the other side. So 5.23 minus 5 is equal to 500 alpha. So 5.23 minus 5 is 0.23 by 500 is equal to alpha. So if I multiply this by 2, I will get 1000. So I multiply the same thing up. So 0.46 into 10 power minus 3 is what I get. Okay. So alpha is equal to 0.46 by 1000. So 0.46 into 10 power minus 3. That's my alpha. Or I can say it's going to be equal to 4.6 into 10 power minus 4. Okay. So either is fine. That's the value of alpha. Now I can use this alpha in the other equation. I can use this or that. Anything can be used. Next one, R2. Because it's all linear, then I can make use of this expression. What is R2? R2 can be written as R0 into 1 plus alpha delta T. It can also be written as R1 into 1 plus alpha into maybe delta T, something else, okay? Because I'm not going to get the same delta T, it will be different. That's why I'm putting delta T dash. Otherwise, either should work, okay? So it doesn't matter. I want to take the first one, this one. Okay, what is R2? 5.795. So 5.795 is equal to, what is R0? R0 is 5 simply, into 1 plus, what is alpha? It's 4.6 into 10 power minus 4 into delta T. I have no idea what that is going to be. Or all that I know is that this delta T is actually this T2 minus T0. What is T0? T0 is in 0 degrees, right? 0 degrees Celsius. So the T2 I'm going to get will be in Celsius. That's it. So I take it in, then be 5 plus 4.6, 20, then 6 into 0.6 into 5, 3, so 23. 23 into 10 power minus 4 T2. Okay, simply T2 minus 0 will become T2. So that's what I get. So if this comes this side, I'm going to get 0.795 divided by 23 into 10 power minus 4 into T2. So that gives me 10 power 4, it goes up, then I'm going to be 0.795 and 10 power 4 will give me 7950 by 23. Okay. So if I do that, I'm going to get 345.65 degree Celsius. So T2 is actually 345.65 degree Celsius. I've purposefully chosen R naught for this. I mean this expression for to figure out this temperature, because like R naught is 5, an easier number to manipulate, and also that the T naught is actually 0 degrees, so it's very easy to do this. That's why I've chosen this expression. You could have done the same thing with the other one, R1. This would be 5.23, and then 1 plus alpha, same value. Then delta T dash would be, now you need to choose T2 minus 100 will be that. Okay, so 0 you get minus 100. So then it will ignore a little bit of manipulation. It may become mathematically a little more difficult to do. So I've used this expression. But you would have used any either this or that. Okay, you would have got the same answer. So this is how you do this. Okay, by the way, I wanted to say something about example 3.3, the previous example. See, when we calculated the delta T in that example, we said it was 823 is what we said. The T2 minus T1, delta T, when we calculated delta T in 3.3, the previous example, we said it's 823, but actually it's 820. So there was a mistake in the when I wrote it. Okay, I think it came as 820.29 or something. Then when I wrote it, I wrote it as 823. So and with that I added this 27 degrees and I got 850 degrees or something. Okay, but it is actually 847. Okay, so that's just a minor mistake that we made in that problem. Instead of 820, we wrote 823 in the previous problem, and then so the temperature was different by about 3 degrees. It doesn't matter. It's not a big amount. So what is more important is how you solve the problem, the method of solving the problem. Okay? And once you know how to solve the problem, then plugging in the numbers and doing multiplication and division can all be done fairly easily and without mistake, if you're careful enough. We weren't careful yesterday, so that's why we made that mistake. Otherwise, that is not a big deal. Okay? So you need to understand how to go about solving the problem first. What are the steps that you would involve? And then go execute them properly. Okay? So the focus must be on how to solve it. And manipulation of numbers can automatically happen. Okay? And if you are good in maths, then automatically that will happen. I hope you understand this problem. It's a very simple problem. It also tells you what you can expect, the kind of problems that you can expect as far as the temperature coefficient of resistivity is concerned. Okay, we'll take up a new topic now, that is electrical energy and power in a conductor. Okay? So in a conductor, let's say you have a conductor here, and there is current I flowing through this conductor. We said that there is a field E set up inside, right? that is field E, set up by the potential difference between these 2 points. So there is a potential difference. If I say this is A and this is B point, then there is a VA and there is a VB potential. Potential at A is VA, V of A, and the potential at B is V of B. Okay? And this potential difference between A and B would be V. That is the voltage of this battery. You will have some potential here, you will have another potential here. So VA and VB are the potentials at these 2 points, and the difference between those potentials will be V. So V is actually equal to V of A minus V of B. Okay. We also said, I want you to recall what we said when we talked about maintaining a continuous current inside a conductor. You just need to provide fresh charges on both sides, so that the electrons inside the conductor will keep neutralizing those charges, and thereby producing a continuous current. Okay, so that's the potential. Okay? VA is potential at this point, and VB is potential at this point, and current will be flowing in this direction, meaning that electrons will be flowing in the opposite direction. Okay? Electrons will be flowing in the opposite direction, but then we will say that the current is flowing in that direction. Electron moving in one direction is equal to a positive charge moving in the opposite direction. Okay. Okay. So this is it. We know AE, we know V, and we also know that I is equal to V E N A. V is the drift velocity, and then E is a charge of electron, and then N is the number of free electrons per unit volume of the conductor, and then A is the cross-sectional area of the conductor. We derived this, and this is what we know now. Okay, now we are proceeding to figure out the energy in this. The energy, dissipated in the conductor. Okay. So once I do this, you will know that you will know how a familiar equation came into existence. But I am not going to give you what the equation is up front. We'll start deriving it, and then you will be able to connect what's going on with what you already know. Okay. So this is a potential difference. And let's say if I is a charge flowing, I is the current flowing through that, which means that in a certain time delta t, okay, certain time delta t, I can get a certain charge delta q, okay, which means that I is equal to delta q by delta t, or I can say that delta q is equal to I delta t. That is, I take time t1 and I start measuring the amount of charge that's flowing in the conductor, and then I stop at t2, then I calculate the amount of charges, total charges flown in that time, and that would be equal to current times delta t, or the current is equal to so much charge in so much time. Right, so delta q by delta t will give me current. So this we know. Now, let's see, when this charge flows there from VA to VB, then what is the change in the potential energy? Well, change in potential energy, okay, change in potential energy, delta W is equal to, so potential energy at the potential energy final minus potential energy initial. So your delta Q charge, it starts moving from higher potential A to lower potential B. So what would the potential, the change in the potential energy of the delta Q charge? Well, the initial potential energy of delta Q charge minus the final, the final potential of the delta Q charge minus the initial potential energy. Okay. So what is the initial potential energy? So delta E, P initial is equal to this potential V A, okay, into delta Q charge. That's the initial potential energy of the delta Q charge. And what's the final potential energy of delta Q charge? So P final is equal to VB to delta Q. Then what's the change in potential energy? That is equal to VB minus VA into delta Q. See, VA minus VB is V. But VB minus VA must be negative V, right? So that should be equal to minus V delta Q. That is the change in potential energy. I'll probably use the symbol delta U better. Okay. So this is a symbol. This is the change in potential energy. It's like this. I have this mass, then it is at some potential energy, its initial potential energy. Then if I drop it, it falls down. So the potential energy decreases. The decrease in potential energy is given by this expression. So minus V into delta Q. Okay, so that's a decrease in potential energy. Well, if there is a decrease in potential energy, there must be a corresponding increase in kinetic energy, right? So what shall we say? So change in kinetic energy from here, as I said, I'm giving an analogy of gravitational field. So change in kinetic energy, the change in kinetic energy is equal to negative of the change in potential energy. So high potential energy comes down, then lower potential energy. So the change in potential energy is negative. That you've gone from higher potential to lower potential. So there is a corresponding change in kinetic energy, right? So the decrease in potential energy must result in increase in kinetic energy. So that gives you this, and that I will say as minus of minus V delta Q, it should be V delta Q, right? Okay. That's fantastic. V delta Q is it's a change in kinetic energy. This is the kinetic energy change. If the electrons were to move freely, the charge were to move freely from this end to that end. Notice here again, when electrons are moving from here to there, but then we are taking equivalent case actually, where positive charges are moving from this end to that end. In reality, electrons are moving this way. The negative charge is moving in this direction, which is equal to positive charge moving in the opposite direction. Okay? So that's what we've taken now. So we've gone from higher potential to lower potential with the positive charge. So there's a change in potential energy, and that must result in corresponding change in kinetic energy. So what should be the kinetic energy caused by this change in potential energy? It is this V into delta Q. Okay? So when there is a change in kinetic energy, notice that it is accelerating, right? It is accelerating, and this must be as it keeps falling, then the speed must change, right? It should keep increasing. But what did we say in the case of this? I is equal to the drift velocity into E and A. So this is a constant speed, rather it's on the average you have a very constant drift velocity, right? It's like charges are moving with a constant drift speed. Right? So that's what you found. Which means that there is no acceleration involved. The speed has not increased. So whatever speed the electrons, the positive charge enters here, is the speed it leaves here. Okay? If it moves with say 5 meters per second, here enters, because of this field, you would expect it to accelerate and then the speed to change here. But the speed doesn't change. We say that it remains the same. It goes there and then comes back and then it starts with the same speed all the time. Because we also said whatever acceleration it gets inside or whatever kinetic energy it gets inside, it goes and hits the ions, the atoms inside the conductor, and thereby transferring the energy it has to those things. So the atoms start jiggling faster. Okay, it's like this. Okay, you have an atom there. Okay, then the electron is moving there, then goes and hits here, then it gets rebounded, but then it starts jiggling. Okay, maybe like this. Okay, it goes like that. This is going to push the next atom there, and that will push this back, so it will start jiggling there. Okay, so because of this this energy, the kinetic energy that the electron has gained by traveling inside the field, it hits the ion or atom and transfers part of the energy, and then it gets slowed down. So whatever energy effectively it gains from this acceleration is transferred to the atom. So effectively it goes with the same speed, same drift speed. It enters with certain speed, the conductor. Okay, the charge enters the conductor with certain speed and leaves the conductor with the same speed, even though there is a field inside. Meaning that whatever kinetic energy it has gained is taken away by something else. I told you that when you do this, if the kinetic energy remains same between initial position and final position, it means that there is another force doing the same amount of work in the opposite direction. That's what I said, right? So this kinetic energy is not reflecting in the charges. Okay? There is no change in kinetic energy because of the presence of the field. Meaning that the kinetic energy is given away to the atoms in the conductor by these electrons. They go collide, transfer the energy, make them jiggle. But as atoms jiggle, what happens? Come out as heat. Okay. So effectively, this is the amount. This is what should have been there. V delta Q should have been there. But there is no V delta Q. There is no change in kinetic energy at all. Whatever kinetic energy it enters, it leaves with the same kinetic energy. Which means that delta Ke is actually 0 for the electron, or in this case, the positive charge you've taken. Okay. Even though there is a field, which means that the work is work done by inside by another force, the collision thing. Okay, is equal to this. That is why it doesn't change, and that comes out as heat. I hope you understand this. I hope this is clear to you. If the charges were to get accelerated without collision, they will get accelerated and then come out with higher speed. And maybe when they go here again, then they will get accelerated again. And when they come here again, they will get accelerated again. So that way, you can expect the current to keep changing from 0 to maybe like infinity. So you can, because it's going to get accelerated more and more and more. So with greater acceleration, you would expect the speed to increase more and more. So if you were to connect an ammeter or something, then it will go from 0 to 10 amps, to 20 amps, to 1000 amps, to it can keep going. But that doesn't happen. You get a steady current, right? You get a steady current, meaning that the kinetic energy has not changed at all because this V has not changed. It enters here with V, it leaves here with V. So the kinetic energy has not changed. But the kinetic energy should have been there. But it is not there. If it is not there, it's because it has been taken away by something else. What has taken it away? The atoms inside the conductor have taken this kinetic energy away and then releasing that energy as heat. So the amount of heat that is produced is equal to V delta Q. Well, that's the energy, right? So that's the energy. So energy that comes out as heat. Energy as heat comes out as heat. That's W is equal to V delta Q. Then what's power? Power is actually delta omega as a delta W by delta T, the rate of change of work here. So you got V here, and then you got delta Q here, and then you have delta T here at the same time. So that gives you V to I. So P is equal to V into I. And from Ohm's law, you know that V, the Ohm's law, V is equal to IR. So this equation becomes I squared R. Okay? So what we understand here is that when I current is flowing through a conductor, then the power loss is equal to VI or I squared R. It's very simple. Even though I've explained it in great detail now, it's very, very, very simple. Pay attention to this, these few lines. When a charge enters, when there is a field, then it will get accelerated. Okay? If there is nothing, if it is like empty, like a conductor or something, if it is completely or if it's empty space, then what would have happened? The charge that enters here would get accelerated and then leave the field. So the kinetic energy would have changed. But the kinetic energy does not change, because we find that the current has a steady speed, Vd, an average speed of Vd, drift velocity. So there is no change in speed, meaning that there is no change in kinetic energy. But it is supposed to have gained kinetic energy, but it didn't gain kinetic energy. Okay? It remained the same. Meaning that the work done here, or the change in potential energy, or the gain in kinetic energy has been nullified by something else. And what is that something else? That is the collision that is taking place inside the conductor. It is not empty space. Now you have atoms inside. So the accelerated charges go and hit those atoms and ions and transfer the energy to them. And that will make the ions in the conductor, the atoms in the conductor, to go to jiggle. Okay. So as a jiggle, that's an indication of the amount of heat in the conductor. Like as a jiggle, they liberate heat. Okay. So the gain in kinetic energy is lost as heat. So the speed of the charges does not change. It remains the same. So there is no change in kinetic energy in the steady current situation. Okay. So and that is equal to this. Energy as heat is this V delta Q. And then power is delta W by delta T. That gives you V into delta Q by delta T, which is I. So you get P is equal to VI. This is an equation you already come across in the lower classes. But now you know why this equation is true. Okay, and by applying Ohm's law, then you also get this I squared R losses. So I squared R losses are the heat losses. Okay, they're equivalent to the kinetic energy gained by the electrons in the conductor but lost as heat. Okay, hope it's clear to you. Okay, this heat loss equation, P is equal to I squared R. It has some consequences. Okay, let me take a case and then explain that to you. So you are at your home and then power is delivered to you by the EB, the Tamil Nadu Electricity Board, and you are going to consume a certain amount of power at your home, and then you will be paying for that power once every 2 months. But where is that power supplied from? The power is supplied from actually Mettur. Okay, so Mettur is where you have the generators, and so Mettur you have the generators. Okay, this is AC. Okay, this is symbol for AC. Don't worry about it now. We'll talk about it. It's like a battery. Consider this to be a battery. Okay, so let us suppose that the battery is at Mettur, okay. And now Mettur is about 60 kilometers from here, Gopchitpalayam. So there must be a conductor, the wires, right, all the way from Mettur to your home. And this R represents the resistance of your appliances. So this is where the power loss is going to take place for you. Okay, and you will be paying for the amount of current you are drawing. And as you draw this current, so let's say this I is the current that you are drawing. Then what is the power loss here? What's the amount of energy that you will be using? That would be equal to I squared R. That's your power at home. And you will be paying for this to the EB. Okay. So the power loss is taking place at your home, I squared R, and for this power loss, you will be paying the EB. But look at the whole thing from the perspective of EB. For them, they have the battery or the generator there, and they have the conductors coming all the way from Mettur through transformers and all that stuff. But finally, they will reach your home. So, but this is all the 60 kilometers here. So you have conductors for about 60 kilometers from Mettur to Gopchitpalayam. And the current, this I that you get to your home, has to travel through this line. You see, the conductors, the 60 plus 60, 120 kilometers, they will have some resistance. Here. I'll call this as R, small r. That's the resistance of R is the resistance of one conductor. So for 60 kilometers, not one conductor. It's a series of conductors, but then I take it as just one single thing as R to your home. And this is again, it has to go back, right, to Mettur. It has to come from Mettur, enter into your house, do the stuff that you want, then it has to go back to Mettur. The circuit has to close like this. Okay? So now, you see, there is this R. The current is flowing through this. And there would be an I squared R loss here. And there is also an I squared R loss here. But notice here, the consumer here is not paying for this. He is paying only for this I squared R. Whatever is happening in his house, not for what is happening here. Okay? This is what he consumes. This is I squared R he is worried about, and he will pay for it. But notice, there is also a loss here, there is also a loss here, and you need to compensate for it by burning fuel in Mettur, or by releasing water from the dam. Okay? So there is a power loss here. I'll say that is, let me take this R and R together, and I will call it as 2R is equal to RC. RC is equal to R plus R. Okay? 2R. I'll just take RC. RC represents the resistance of the lines. Okay, so this is RC. Okay, the power loss in the conductors is going to be this, right? So PC in the transmission is equal to, say, I squared into RC. Okay. Now, how can I write this I squared? Well, let me go to this place. See, here P is also equal to VI. V is the voltage across this one. Voltage you receive at home. So V into I. From there I can say that I is equal to P by V. So it's the same current which is flowing through the entire circuit. So this can be written as I is equal to P by V, the whole squared into RC. So that gives you P squared by V squared to RC. That's the power loss. So this is the power loss that is going to happen. When I supply I amperes to your house, this is the power loss I am going to suffer in transmission. Okay? How can I minimize that power? Look at this equation. So this is the power I am going to supply. That's all right. Okay? Which means that this cannot change. Your appliance requires this power, 70 watts or 100 watts or whatever. Okay? Your appliance requires this power to function. But notice here, suppose if your appliance works at a higher voltage, if you can increase V, okay, then this denominator becomes a bigger number and PC will become a smaller number. So it always pays to transmit power at a very high voltage than a low voltage. And that is why when they transmit power from A to your house, they will have transformers and stuff, 220 kV and 11 kV transformers, 22 kV transformers, 110 kV transformers. You can find them, different types of transformers. We'll study about transformers later when we study alternating current. But understand that it is always useful to transmit power over long distance at a higher voltage. That reduces the amount of loss you will suffer in transmission. No one is going to pay for this, so you have to reduce this. You have to keep it to a minimum. Because the consumer is going to pay for only this. Okay, you will pay for only this, your neighbor will pay for only what's happening in his house. He is not going to pay for what's happening here in transmission. Okay, so that is the reason it pays to transmit power at very high voltages. You can see that from here. The voltage is high, then the power of transmission will be small. Okay. Hope this is clear. The other topic that we will take up today is resistors in series and resistors in parallel. This is something that you already done in your 10th standard, but I'll do it anyway here. Okay? So resistors in series and resistors in parallel. First I do resistors in series like this. So you have resistor here R1 and then you have R2. So this is R1, this is R2. And let's say that there is a current I that flows through this. Okay. So then I into R1, this will give you a certain voltage V1. Okay. and the same I flows through this and into R2, that gives you voltage V2. Now what is the total voltage? V1 plus V2. Yeah. So total voltage V is equal to V1 plus V2. So this is equal to what is V1? I into R1 plus I into R2. That gives you I into R1 plus R2. This is the same as another case, right? That case is this. I have a single resistor. I is flowing so R, and the same current I is flowing through it. Then what would be the voltage drop across this? This voltage drop must be equal to this voltage drop. Okay. So V here is equal to I to R. So this is 1 and this is 2. Okay. So now this R, if the voltages are the same, then I can say that 1 is equal to 2. Then I will say IR is equal to I into R1 plus R2. Then I and I will cancel. And I will say R is equal to R1 plus R2. So here R is called as the effective resistance. So likewise, if I have a third resistor in series with these two, then again I will have V1, V2, V3, and I is the current which is going through all the three. So the total voltage V can be will be equal to V1 plus V2 plus V3 there. Okay, and again the equivalent resistance R will be equal to R1 plus R2 plus R3. So in general, if you have n resistors connected in n resistors connected in series, then effective resistance R is equal to R1 plus R2 plus R3 all the way up to Rn. Okay. So, but first of all, what is effective resistance? If you understand that, then this will become much clearer. Okay. It's like this. Effective resistance is something like this. I have a circuit, say let's say V, that's a voltage, and then I have resistor R1, and then resistor R2, and then resistor R3, and maybe resistor R4. All these things have been connected in series. Okay. Whenever I talk about effective resistance, this is what I have in mind. I'm going to replace the entire circuit with just one resistor, like this. Okay, this must be equivalent to one battery here and one resistor here. B into R. I'm going to replace the entire thing with just this. If I do this, the question here is, what is the value of this resistance? What is the value of resistance which will draw the same current I from the battery? So whatever be the complexity of the circuit, whatever be the circuit here, this is going to draw a current I, a certain amount of current, 10 amperes or whatever. My question is, if I replace the entire thing with this one resistance, then the battery I have here, I'm going to have the same battery here. That should supply the same current if I connect it between these two points. So whenever they ask you to find effective resistance, keep this in mind. If you want to figure out whether resistors are connected in series or in parallel, you just have to keep just this thing in mind. The effective resistance can be found only when the 2 points are specified. Okay. A, B. For example, I can say this is A, this is B. When those 2 points are specified, you need to understand that you are going to connect the battery between those 2 points. Okay? If you connect the battery between those 2 points, then the battery is going to supply a certain amount of current. And that current must be the same if you remove the circuit and put one resistor there. That's effective resistance of that circuit. It should draw the same amount of current from the battery. Think about it this way. You are in charge of metro power station. Okay? What would you be interested in? Well, you would be interested in how much current is going out of your power station. Right? You have a generator, or maybe a few generators. Let's make it simple. You have a generator, and that generator is going to get connected to so many houses. Are you going to get into the details of what is happening in each and every house? You would not. What would you be interested in? You would be interested only in the amount of current that is going out of your power station, your generator. So for you, all the other circuit, the complex circuit you have out there, some houses will have 2 TVs and then like 10 bulbs, and some other houses will have 5 bulbs and then 1 TV and then a fan, stuff like that. You don't want to get into such details. You don't know what's going to be. You don't want to know the details of what's happening in every house. As far as you are concerned, this is my generator. It produces this voltage. What's the amount of current that is going out of it? So if you know that, then I am confident. I can calculate the power output, how much power I am supplying, how much energy I am supplying, and based on that, I can plan for how much coal I need to buy to run the thermal power station, or I would know the amount of water I need to store to keep supplying this, how much water I need to keep supplying this, and how much water I should spend to support this. So you will be concerned only about that. You are not concerned about what is happening in individual houses. So for you, all the houses in Tamil Nadu are just one resistor connected across your generator in metro. Okay? And equivalent resistance is something like that. You don't care about the complexity of the circuit out there. As far as you are concerned, I am going to replace the entire thing with one resistor between these 2 points. Once the points are specified, I am going to replace the entire thing with just one resistor, and I will connect that to a battery. And I should get the same amount of current in either. Okay? So that is effective resistance. And this is how you find it for series connection. We'll do the same thing for parallel connection. Okay, now we'll talk about resistors in parallel. Okay, so let's say I have 2 resistors in parallel. This is R1, this is R2, like this. So what I'm going to do, I'm going to connect these two to battery. Okay, V. So what are the points I'm interested in? I'm interested in these points. Point A and point. This is my point A and point B. And with reference to these points, these resistors are in parallel. See? Because I'm going to connect this battery, right? What is my intent? I'm going to replace this with a single resistor R. Okay? The same voltage, the same battery is connected here. I'm going to replace this with a single resistor, the 2 resistors, and this is going to be my A, this is going to be my B. When I do that, this battery should supply the same amount of current as it was supplying here. Then what should be the value of this? That is the equivalent resistance. Okay. Okay. Now let's do this. Let's say this is I. I will go and then it will split into two things. I1 will go here and then I2 will go here. I goes there. I gets split into I1 and I2. So I is equal to I1 plus I2. Okay. Now, so what is the voltage here? This is V, right? It is same as this. These 2 points. So I1 R1 is equal to V. Same voltage, right? It won't get split anyway. It's equal to V. So I1 is written as V by R1. And then we do the same thing for I2. Okay. What's the voltage across this resistor R2? That is I2 into R2. And that should also be equal to V. You see, you're connecting it to the same 2 points A and B. There is nothing in between. Just Y. Nothing in between. Okay. So this is also equal to V. So here I2 is equal to V by R2. And what is I here? I here is equal to I1 plus I2, which is equal to V by R1 from here plus V by R2 from there. Okay. Now what did I say here? I must replace the whole thing with another resistor R so that this V, this battery, supplies the same amount of current there. So what is the voltage drop across this? That should be equal to I into R. So I into R is equal to V, right? So here I must be equal to V by R, right? And I told you that this I must be the same as this I. So what does it give you? That gives you V by R equals V by R1 plus V by R2. You remove V's and I have 1 by R, 1 by R1 plus 1 by R2. Okay. So even if I have one more, then I will say I is equal to I1 plus I2 plus I3. So where I is the amount of current that is coming out of the battery. That should be same here. So in that case it will be R1 plus R2 plus R3. And if there are more, there are n such things, there are n resistors in parallel, then this will give you 1 by R is equal to 1 by R1 plus 1 by R2, 1 by R3 plus 1 by Rn. Okay. So this is how we calculate the effective resistance of resistors in parallel. Hope this is clear to you.